Hello, everyone. Let me screen share. We're good. Sydney, I figured out the answer to your question. The problem is the key for Y and the key for 7 are very close to each other. Did you know that? So if you accidentally meant to type in a 7, you might accidentally type a Y instead. Here we go. All better. I was really confused by your question.
I was
Like,
looking at that for like
what?
hours.
For hours? Oh, don't do that.
I was like, it's like I don't like leaving things like unfinished or like
Oh,
unsolved. So
good.
I'll go through and do it. But then like I couldn't get it. I was like, shouldn't there be something on the other side at least? Because
Yeah,
I
yeah. I'm not giving you differential equations in this class. Not hard ones, at least. We won't even call them differential equations. Well, I'm sorry to have wasted your time. Hopefully you learned something through this thought experiment. Try to figure out what that means. Later you can take multivariate calculus where all those things are reasonable to think about, but not in this class. All right, is it time to start? Almost time to start. Oh yeah, it's time to start. Well, everyone, you guys are doing well. Just a reminder, there's no class on Monday, especially for you online students. We have MLK Day activities on campus. All right. So I just want to recap what we've been doing. And basically we're doing, well, for a few other little announcements before I get carried away with the math. I hope to post a homework for you this afternoon for Wednesday of next week. So if you're like, I just need to do homework real bad, now you'll have something to do. You may not be able to do all of it at first, but you should be able to do it. And yep, we will have calculus at night help sessions with Andrew. You're out there, right? What time are the help sessions? 7:30 to 8:30 on Tuesday, right? Okay, let's write that up at the top here. Just in this classroom, calculus at night. 7:30 to 8:30 Tuesdays. Okay. So that's that. One other thing to mention is that there is a web work site for this class. I haven't assigned you any web work yet. But one thing to know is that it's not the same web work page as before, which means that whatever password you had last semester is gone. Your user ID, again, is the last 5 digits of your student ID, and your password has been reset to the last 5 digits of your student ID, okay? Well, if you never changed your password, yes. But of course, you should change your password because hackers can break into your homework and do it for you. So you must change your password so that the hackers don't do your homework. That would be really weird. Okay, any questions? We are going to continue reviewing essential material from last semester. There's a lot of things we covered last semester. I mean, we did a lot of things with limits, a lot of things with topics and pre-calculus especially. We're still going to do some pre-calculus things, but not quite as much for the second half of the semester. But many of the things we did, like when we would remember when we would figure out the derivative by taking h to 0 and all that? We're not doing that anymore. That's over. It's gone. We'll have other tasks that are similar to it later, but we're not going to have that. So well, I'm not reviewing everything because we don't need everything. Now, a lot of those topics, though, that we did cover in the first half of the course They are needed for like later math courses, like much later, like multivariate calculus. So it's not a waste of time that we covered it, but it takes you don't necessarily see the payoff for it until later on. So let's just recap. We have all our differentiation rules here: product rule, quotient rule, chain rule, general power rule. We went over derivatives of trig functions. And then I left you with a problem to work on. These problems. And I believe most of you got pretty well through at least part A, and I did part C here. I promised I would do part D. So let's warm up by doing part D, and then I'll leave you to finish these, and then I think we'll be able to introduce a new topic today called implicit differentiation, which is kind of funny because I'm having to like have my differential equations class review that as well. So sometimes topics overlap a lot. There we go. That's better. So this is part D. As you can see, I made a slight edit. There is a 7 in the denominator there instead of y. Y and 7 are very close on the keyboard. And in my haste, I accidentally typed the wrong thing. But let's go over how to do this one. So we have to take the derivative of, well, we have this 2/3 sine the 3/2 of t. Now, when we write sine to the 3/2 like that, just a reminder, what that really means is that. So with that in mind, what rule do you think we should use to take that derivative? Yeah, the general power rule. This one is vital. So the general power rule says when you take the derivative of a function, g to the nth power, that's its derivative right there. So I'll have, just keep the 2/3 in front there. My n is going to be 3/2. So I'll have the 3/2 come down. And then it'll be sine of t to something. What will the something be? Yeah, 3/2 minus 1, which is 1/2. And am I done? No, I gotta multiply it by something. Do you know what it is? I think Sydney's telling me. Yes. Sydney typed cosine. And why is that? Well, in this general power rule, our g of t is the sine, and the derivative of sine is cosine. All right, let's move on. The derivative of sine to the 7/2, can you guess what that's going to be? Okay, just move that 7/2 down. What will the new exponent of sine be? 5/2. And what do we do next? Cosine t. And that's it. You leave it like this, though I wouldn't lie, I'd be a little disappointed if you did, because there is a trivial simplification. 2/3 times 3/2, that's just 1. And so you can write this as the following. And that's it. So really we're just using all our rules again to take derivatives. So that's just to kind of warm up there, remind you a little bit of how this process works. I will leave this up here and you can continue on doing even more fun math problems. I know review is not always fun. It's not, but it must be done. There, I cleaned it up a little. Just a little. Oh yeah, and didn't he ask me questions? But if it were why, how could you even do it? I'm curious. Oh, uh, it would be complicated. It would be complicated. It depends. It depends, Sydney, on whether why depends upon t in any way. So if y were to change with t, then you should think of y as a function, in which case you'd have to use the quotient rule there. But if y were not a function, just some other variable that doesn't change with t, then you could treat it as just essentially a constant. So that's the short answer there. How's it going? You forgot a pencil. Yeah, you know what? I keep a stockpile of those in my office, so I will loan you a pencil. Or you can have it's my gift. Here you go. You have a sweatshirt with your last name. Like a family reunion thing or
It's got like
really? Oh wow. Okay. The Bate family has a proud heritage. Well, not entirely proud. An interesting heritage. An interesting heritage. My great grandfather was working the railways in Texas, and he made his fortune by suffering an egregious accident. I think he lost his arm, if I recall correctly. But with that money, he built a giant mansion. And the family would have lived prosperously from then on had he not gotten drunk and accidentally set it on fire. Easy come, easy go, my friends. Let that be a lesson to you about the dangers of alcohol. I should probably look that up to make sure that story is true. I'm pretty sure it is, but I remember learning that one as a kid and being like, I don't know if I should be like proud of that or not. I had a grandfather who was slightly crazy. I mean, he wore a white jumpsuit every day. I don't know why. He just did. I remember as a 5-year-old thinking, something's not right. I don't know what it is, but something's not right. But he loved doing genealogies and he traced our ancestry back to William the Conqueror. A long ways back. How's it going?
Look at it.
Well, here I got an answer somewhere. So you are doing F. Okay, yeah. So what rule are you using on this one? I don't think you wrote down H. I don't think you wrote down H correctly. It's a T times tangent T. It's a little hard to see. Is that better? Negligibly better? Here, we'll hide this. There. I'll unfreeze it there. Yeah, that should be easier to read. How's it going, Keaton? That's good. What rule? It looks like you're doing the product rule. Good. It's exactly the rule to follow. April, I hear you're going to take data science for beginners. One of my friends in college is teaching that. He's very accomplished. Did you know that? No. He was one of my friends and he went to Harvard for his PhD in biostatistics. And then he was a professor at Brown for a long time. And then and now he's the chief statistician for a pharmaceutical company. So I can't believe we got him to teach that course. He's the most overqualified online instructor we've ever had. Dramatically overqualified. How's it going? That's an interesting looking pen.
Yeah, I don't know where I just found this somewhere.
Oh, okay. Well, yeah. And oh, I forgot to see how you're doing. Are you doing? Okay. Oh, you're doing the tangent line problems. Good. How's it going, Keelan?
Good.
Isn't it?
Is this supposed to be a point? It's supposed to be
No, well, you don't actually have to do any algebraic manipulations with this. You can just use the quotient rule on this first part. Yeah. Makes it a little bit easier. Yeah, you're like the second derivative. Yeah, what you have to do is do the product rule on this part. And so you'll have to figure out what the derivative of secant squared is, which requires using the general power rule. It is a painful problem. Secant tangent. And it's up there. It's up there. My mouse is a little bit over it there, but well, the weather looks miserable today, doesn't it? Oh. Yeah, want to go over F, everybody? It's a trickster. It is like an everything rule. Like you're like, surely it's just one problem, but it's not. Okay. So yeah, let's discuss that. So first step is to recognize that it is a product, right? There is a t here, a negative t there, and a tangent of t there. You could call that your u and that your v. And then the tricky part is remembering what the derivative of tangent is. It's up there on the screen just above, but it's secant squared. So we would have a u and then a v prime. In this case, our v prime is secant squared of t plus, and then I have to take the derivative of u. The derivative of negative t is -1 times tangent of t. Does that look okay to people? All right, so that's not so bad. And just pretty it up a little here. Not that much. The hard part's taking the second derivative. The second derivative is involved. And as much as I love Leibniz's notation with the d squared h over dt squared, I'm going to just write h double prime of t if that's okay with you. So what rule should we use here for this t secant squared? What's a good rule to start with that one? The good old product rule again. Yeah, we're gonna just let that be our u. U is gonna be negative t. And our v is going to be secant squared. Now, one of the tricks of the trade is to allow yourself to write things like the following. So here I'm writing down u, right? What should follow is a v prime, but I don't know what v prime is right away. And so it's fine for me to write this. Say, take whatever the derivative of v is eventually. It's like a reminder to myself, oh yeah, I should take the derivative of that eventually. This is, just to recap, this is my u, this is my v prime. And by doing that, it allows me to write out my work more fluidly. And then I will add to this the derivative of u prime, or the derivative of u, which is u prime, times v. There we go. And so this is, what was that? Did you see that? OneNote started getting fractally on me. Weird. All right. Oh. So this is, this all here, all of this stuff is really just the product rule on that one thing. And then what else have I to worry about? Am I done? Did I get h double prime? No. Oh, I don't know the derivative of secant squared yet, but I haven't taken the derivative of this tangent term yet. Okay. So at this point, it's good to have like a little interlude where I work out, well, that's a very thick pen, isn't it? Let's tone it down a little here. Let's figure out what this derivative of secant squared t is. What rule should we use for this? Wow, that looks, I mean, I don't mean to distract you looking out the window, but doesn't that look just terrible? I don't know if you could see it, but it's like gusting sleet snow at people. It's apparently it was really windy last night. Did you guys lose power out here? No, no. We almost did in our house, almost.
We lost power.
Oh, you lost power? Yeah, they started crying because the YouTube turned off for a second. They're like, oh no, the YouTube is gone. What are we gonna do? Learn math? No, not at this point. Well, Eli could learn math. He's in 8th grade. He likes solving linear equations. He just doesn't like writing down his work. I have to work on that with him. All right. So, okay, yeah. What rule should we use? General power. Okay, the Keaton's bored. He's like, come on, man. All right, so I do 2 times secant t, and then what's next? Whatever the derivative of secant is, right? And what's the derivative of secant? Secant tangent, yeah. Okay. All right, very good. We are learning math. And of course, you got 2 secants there. I mean, you might as well write this as 2 secant squared t tangent t. There. And then I'll go back to h double prime now. H double prime of t is now going to be a negative t times this 2 secant squared of t tangent t. And there's that -1. I'm going to just write that. That would just be a minus secant squared, right? And do you see what happens? There's another minus secant squared. I'll just call this minus 2 secant squared. There we go. That's the second derivative, everyone. Good thing we don't have to do too many of those in life, huh? In this course. In this course, at least. All right. Any questions on this one?
Explain how the secant square changed.
Yeah. So first of all, I want to be clear. I'm doing this derivative because I need to figure it out for this part. Does that make sense? Yeah, so this derivative of secant squared, I'm just like, oh, I don't want to write it out every time it's a lot of work. Does that answer your question? Okay. Yeah, otherwise you're like, he changed colors for some reason, started doing a random problem. Just another day in calc with pre-calc. Okay, any other questions? Okay, I want us to review one final topic that's essential for the rest of the course. Oh wait, I see something in the chat. I wonder if it's, I need to go turn off the heater. I'll be back. Okay, no problem. We all have to turn on and turn off heaters from time to time. I have a water boiler. I have to relight constantly. I was thinking about getting it replaced, but then I thought about money. Decided I liked my money and I didn't mind relighting it after all. You know how that works? All right. Yeah, I want to keep it. All right, does anyone remember, how do you find the equation of a tangent line? Like, what's the formula for a tangent line? Like if I say, give me the tangent line through f of x at x equals a, do you guys remember what it'll be? It'll be like a y equals, and then what? Yeah, or if you want, you can write f prime of a, because it's the slope of the tangent line. And yeah, it'll be x minus a, and you could do a plus b, but because we want it to go through the function at a, it's just an f of a here. So basically, these problems are just asking you to, essentially, if you wanted to, these are your a's here. Try those out. Try finding some equations of tangent lines. And if you have nothing to do in the interim, I'm sorry. Just hang in there. We'll do fun stuff in a little bit. Eventually we'll get implicit differentiation, and I can show you some pretty cool things. It's Korean, I think. You don't know what it is? I think it's Korean. You got a Boston University shirt, sweatshirt. Is that Boston University or no? I thought I saw university there. So I lived like 3 minutes from Boston University at one point in my life. Nice place. Very crowded though. So in part A, your f of x essentially is x plus 3 squared. I don't know if that was obvious. All right, I tried to make it a little confusing by calling it y. That's just to mess with you. That's the only reason it's there. All right, did anyone figure out what the derivative of this was? What's the derivative of x plus 3 squared? Cubed, yeah, cubed, yeah. What's the derivative of x plus 3 cubed?
3 times x plus 3 squared.
Yeah, that's it. You might be thinking Keaton has messed up because he forgot to multiply by the derivative of x plus 3. But the derivative of x plus 3 is 1, so we're fine. All right, next we need to figure out what our f prime of a is. And our a in this problem is essentially -2. So if I plug -2 into here, I get 3. And then last of all, I just need to plug 2 into my original function. This will give me -2, -2, totally different problem. Yeah, -2 into my original function. And I'll get 1. And so the derivative for my tangent line is 3 times x minus a -2 plus 1. Are we okay with that process? What was that? Oh, okay. Want to move on to implicit differentiation? You're like, look, I had enough of last semester, Brandon. Let's liven things up. I agree. Let's do that. Just need to drop a slide in here. I forgot to do it earlier. I got thinking about a math problem, which is basically like, I will lose all track of time once that happens. Okay. All right, this is going to be called implicit differentiation here. I should send a copy to everyone. Yeah, let's distribute this. Distribute page to notes. All right, there we go. All right, so implicit differentiation. Okay, so we've been working with functions. A function looks like this: y equals f of x, and f of x is stuff with just x, no other variables. You recognize that's what we've been doing? Those are the functions we've looked at. We know how to take derivatives of functions like this. But there are other types of algebraic expressions out there in the world. So below I have a plot of a curve. Do you see this curve? It's kind of unusual. Does this curve give a function? No, it fails the vertical line test, right? If I draw a vertical line, if it's a function, it should intersect the vertical line at only one point. But here, if I drew a vertical line, sometimes it would intersect at 2 points. So this is not a function. And part of the reason is, you can see it here, I don't have y equals stuff with just x's. I have something awful looking. I have y squared equals stuff with x's, and there's a y there just to mess around with me. And so what I get is a curve that's not a function at all. But what's interesting to think about, though, is the fact that even though this curve is not a function, if I were to pick a point on the curve, it still has a tangent line. Like, those tangent lines still exist for the most part. And so the question becomes, how do I find the equation of a tangent line at a point on a curve given by an equation that's not written as a function? How do I do that? How do I figure out, in particular, the slope of the tangent line? So here's kind of a prototypical type of problem. You're given some sort of equation with x and y's, and you're given a point. In this case, the point is the point 0, 2, and you're asked to find the equation of the tangent line through it. And of course, generally speaking, right, if you want the equation of a line, so we were just talking about, in general, the equation of the line is y equals m times x minus a plus b. And in this example, our point AB that the tangent line goes through would just be this point 0, 2. The problem for us is we have to figure out what the slope is. And the only way we know right now to figure out the slope of a tangent line is to have a function, take its derivative and evaluate the derivative. But this thing is not a function. So what do you do? All right. Well, I will tell you what we do. We pretend it's a function. We're going to pretend it's a function, sort of. So long as you are not colorblind, you should see this blue curve here. And do you notice this red thing here? That little red portion I highlighted? Is that a function? Well, yeah, technically. This is a function right here because it passes the vertical line test. And so theoretically, I can think of this portion of the curve as being a function of x. Do I know what that function is? No. No, if I were to go back to my original equation here, this y squared plus x cubed minus x squared minus xy plus 4, and attempted to solve for y, I would become a bitter, angry person. It is not easy to do. It's not straightforward in any way whatsoever. So finding out what this f of x is exactly is impossible for us in many cases. So if you're thinking to yourself, all right, Brandon, I can see that you've identified a portion of the curve that clearly is a function. The only problem is you can't tell me what the equation for the function is. Yes, that's correct. There is a function here. I don't know what it is, and it's almost impossible for me to figure it out. But let's just go with this for now. So what that means is as long as I'm looking at this red portion right here, my y is in fact a function of x. And so for points on this red portion, I have the following being true. Wherever I had a y in my original equation, I can replace it with an f of x. Again, I'm just looking at the red portion here. And so I have f of x squared gives me x cubed minus x squared minus x times f of x plus 4. Okay. Now, just to recap, I don't know what f of x is, and there's almost no hope for me figuring it out. But I'm going to tell you what the derivative of f of x is right at that point. I'm going to figure that out. How? Okay, here's the idea. And I have all the math written here on this slide. You're going to have to look at the bottom of it because I want to reveal it. I want a slow reveal here, right? I don't want to show it all at once. So the idea is we're pretending we're on that red portion, and what we're going to do is, even though we don't know what f is, we're going to take the derivative of both sides of this equation. And so I'm going to take the derivative of f of x squared, and then I'm going to take the derivative of this x cubed minus x squared minus x times f of x plus 4. Now, I can use the general power rule here to take the derivative of f of x. We've written that a few times now, and hopefully you remember it. I'm just going to move that 2 downward. So I have my f of x here. I have it squared. I just move the 2 downward. I get 2 times f of x to the 2 minus 1, which is just 1. So I didn't write the 1 exponent there. And then I multiply by the derivative of f. And so the general power rule is very convenient. It basically tells me that, well, whatever this left-hand side is, it's going to be 2 times my function times f prime. Well, what about the right-hand side? Well, a good chunk of it's easy to figure out, right? We know what the derivative of x cubed is, right? That's going to be like 3x squared. The derivative of x squared is 2x. There's this thing. What's the derivative of x times f of x? I don't know. We'll get to that later. And then the derivative of 4 is 0. So, I could take that derivative, okay, except for this x times f of x. And normally at this point, I'd ask you, what rule should we use to figure out this derivative? But I think you can read. Yes, I have it on the slides there. The product rule. We will use the product rule. So you can see here on the slides, I have this 3x squared right there, minus 2x right there. The derivative of 4 is 0, and apparently I thought it was worth writing 0 there. You can disregard the 0 from here on out. And now I have to take the derivative of x times f of x, and yeah, the product rule is exactly what I use. I will get a 3x squared minus 2x. I'll take the derivative of the first term, which is my x, times f of x, plus x times the derivative of my f. And the derivative of my f is just f prime, and the derivative of x is just 1. And so I'm left with, in parentheses here, and it's important to remember the parentheses when you use the product rule, everyone. That's really important. Otherwise, it's wrong. All right. I get f plus x f prime. And so when I simplify this a little bit, I end up getting 3x squared minus 2x minus f minus x times f prime of x. And so I can put it all together here. This equation up here, I have this left-hand side there. This left-hand side is the same as that. And so the left-hand side, the derivative of f of x squared is just 2 times f of x, f prime of x. And as for the right-hand side, I have shown that the right-hand side is the same as this. And so those are equal there. And so the moral is, at this point, I've taken one ugly equation, differentiated it, and got yet another ugly equation. This is what we call progress. Okay, we are making progress. Now, what's interesting is I can now solve for f prime of x. And I have the work here on the slides, but I am going to work it out on the side here, just so that we can think about it together. So I have this equation 2f of x, f prime of x equals 3x squared minus 2x minus f of x minus x f prime of x. There it is. That's that equation. And what I want to do is I want to figure out what f prime of x is equal to. And so I start by identifying all my terms that have an f prime of x in them. All right, does anyone remember from algebra how we solve for something in an equation? Like, what's the general approach we should take? Yeah, we want to get all the terms with an f prime on one side of the equation, right? And so right now I have a term with an f prime on the left and a term with an f prime on the right. And so what I'm going to do is I'm going to add an x f prime of x to both sides. And when I do that, it's going to cause this positive x f prime is going to cancel right there. And so I will get 2 times f of x, f prime of x, that's my first term, plus the second term, x f prime of x, is equal to 3x squared minus 2x minus f of x. And just to recap, here's where my f primes are right there. All right, does anyone see how we solve for f prime? What's like the next thing we do once we get all the terms with what we're trying to solve for on one side? What's kind of the next thing? Yeah, we could group, we see that there's an f prime in each of these terms, so we can factor an f prime out of both terms. So we can write this as 2 f of x plus x times f prime of x. All right, and so, you know, in high school, we often give problems like this. We're like, multiply this sort of thing out. Stuff in parentheses times something outside it. Here we're doing the reverse. We're taking a bunch of things and being like, hey, I can factor an f prime out of all this. And then divide, yeah. And so now I've sort of figured out what my f prime of x is. I've figured out that my derivative, just for that red portion, is this thing. Now there's just one problem though. The one problem is I don't know what f of x is still. So you might be saying to yourself, well, Brandon, you found a nice formula for the derivative, but it's still kind of useless because you don't know what f is. So how are we supposed to use this to find the slope of the tangent line? And basically what I'm going to do is I don't need to know what f is. I could still use this formula without knowing what it is exactly. And so to explain that here, let me lasso this and make a copy of it so I have ready reference to it. All right, so if you follow the slide here, you can see I get basically the exact same formula right here. So, oh, I don't like the way I wrote this. Okay, let's go back up here. Back up here, we're looking at this f here. All right, just in that red portion, I have a question for you. What is f of 0 equal to? 2, all right, yeah, you see that? Right? Okay. And the slope of the tangent line at the point? So the slope of the tangent line at 0, 2 is whatever f prime of 0 is. Do you buy that? So I have a little function f of x. This 0.02 occurs when I plug 0 into my f. So whatever the derivative at 0 is, that's going to give me the slope of the tangent line at this point. And so here, let's take a picture there. And so if we go back to our work here, this is pretty neat. It's kind of enormous. Yeah, what I could do now is with this observation in mind, I can now just plug in for x equals 0. And so I'll get a 3 times 0 squared minus 2 times 0 minus f of 0 all over 2. I said f of 0 is equal to 2. I don't know what f of x is. The only thing I know about f of x, and thankfully it's the only thing I actually need to know about f of x, is that when I plug 0 into f, I get 2. Yeah. Negative 1/2. Unbelievable. And so, even though we never figured out what f was, unbelievably, we could still figure out that the slope is negative 1/2 without ever figuring out what f of x is. The reason why it's called implicit differentiation, and that's what we just did, is because we never had an explicit formula for f. We just sort of figured out what the slope of the tangent line would be, sort of by doing this kind of clunky process. So just to recap, what we did was we replaced y with f of x. We differentiated both sides, and then we solved for f prime. And after we solved for f prime, we evaluated at the x coordinate of the point of interest. And so now we can get the equation of the tangent line. The equation of the tangent line here is the following. So this will be -1/2 x plus 2. And you could check it by plotting it if you wanted to. So I realized that was a lot of information there. This is a bit of a more complicated problem. So I'm going to give you a problem to work on. Just be aware, I'm going to show you a slightly different way to do these next class. Slightly differently. The way I'm teaching you right now is kind of a semi non-standard way, but I will show you the standard approach in a little bit. Students tell me this helps them not get it wrong, okay, the way I'm teaching it, where I replace y with f of x. A lot of books don't bother doing that. Okay, so let's try working on number 1 here. You're given this equation 3y squared equals x minus xy, and you want to find the tangent line at 4, -2. So our first step, step 1, is to replace our y with an imagined function f of x, and then take the derivative of both sides of this equation. You're going to have to use the general power rule. You're going to have to use the product rule. After you do that, check with someone to make sure you know you're not way off. And so you'll do that, differentiate, and solve for f prime. Okay, go ahead and have fun doing that. And I'll plot this curve for you so you can see it. You know what? Ever since we lost Hallie, this place is a lot quieter. Have you noticed that? Whole lot quieter. Hey, and what happened to her friend, Mara? Hold on, she signed up for this just for the first time? Oh, she's in London. Oh, man. Is Hallie in London? No. She's still here. That's right. She just needed this for Gen Ed credit. The hardest way to get your Gen Ed math credit, if you ask me. But how goes things? It's going, sort of. So now just take the derivative of the left-hand side using, is that a 6?
Yeah.
Oh yeah, it would be. But these aren't technically equal to each other. Like you want to like start a new line.
Yeah, okay.
So it'll be 6f of x, but then there'll also be an f prime of x because of the general power rule. Yeah. How's it going? I'm here to spy on you. Very good. Okay. Yeah, good job looking back at that. That's a good idea. It's oh yeah, you did it right. But except for the parentheses on the product rule. So you just need to put a set of parentheses like right there. How's it going for you, Connor? Okay, yeah. Oh yeah, good parentheses. Never forget parentheses. They are not optional. you want to see a plot of this, here's what it looks like. This is what 3y squared, let me make it. This is what 3y squared equals x minus xy looks like. You can see it's not a function at all. And this is the point right here at 4,2, where we're trying to find a tangent line. Trying to find the equation of that tangent line. How goes it? Okay. Here, I'll write out the next step here. Oh wait, I got a chat message. I believe I found it. Here, let me check my answer key, Sydney. Let me check. Oh, I have so many things in calculus in this notebook. My goodness. All right, did you find the slope of the tangent line? Find it? I don't know. Maybe. That's right. Good job. You can always check your work too on these by plotting the curve, plotting what you think is the tangent line, and seeing, is it even remotely close? All right, let's discuss how to do how to get started on this. So did anyone figure out what this left-hand side is? What this left-hand side turn out to be? Almost. So we're going to have to use the general power rule, right? So you can think of that 3 just sort of being out in front there. And then if we were just, looking here, what's the general power rule when we use it to take the derivative of f of x squared? We move the 2 down, we subtract 1 from the exponent, so we'll get a 2f of x, and then there's one more thing we must do. Times f prime of x, yeah. And then the derivative on the right-hand side, so the derivative of x is 1. And then we have to use the product rule to take the derivative of x times f of x. So if you haven't done that, try that out. And yeah, I'll leave this up for just a little bit here. And Bina, for this one, yeah, let's work this out a little bit more. So if I do the product rule here, I gotta make sure it's in parentheses. I'll take the derivative of x, which is 1, times my function f of x, plus x times f prime of x, like that. Do you see how I use the product rule there? Here, I'll write it out a little bit. So this is my u, this is my v, u prime v u, and this is the v prime right there. And so, okay, now I've differentiated both sides. 3 times 2 is 6, so I don't need to worry about that. And I'll distribute this negative across, so I'll get 1 minus f of x minus x times f prime of x. And I'll highlight my f prime of x terms. Okay. And so what do we do next? Well, everyone calm down, not all at once. No dividing yet.
Add the x times f prime of x over to the other side, then factor out the 6f of x and then the x, then the f prime of x. Then you can like divide them, and then you can just plug in those numbers.
Correct. I had 2 people answering the question at once. It was great. Both of them, same time. Could not hear each other though. All right. All right, so I get the f prime of x terms on one side. I can now factor the f prime of x out of both of those. Like that. And now I can solve for f prime of x. And I do that by dividing by this left-hand term. All right, and now Lee's question is, what value of x do I plug in? All that to answer your question, Lee. So first, I need to kind of go back and recall where my point is. So my point is at 4, 2, right there. So since point is at 4, 2, then I imagine that my function is such that when I plug 4 into it, my x coordinate, I get out 2, my y coordinate. Oh, I guess it is a -2, yeah. I just wrote the wrong thing. There we go. And so now I could figure out what the slope is at that point by, can you guess what number I plug in? 4, yep, yeah. I plug in 4, I'll get 1 minus f of 4 over 6 times f of 4 plus 4. All right, now f of 4 is -2, so I'll have a 1 minus a -2 here. I'll have a 6 times a -2 plus 4. If I simplify that, I'll be left with a 3 and a -8. Well-adjusted people write -3/8. There we go. And so that gives me the slope of the tangent line. Now, how do I get the equation of my tangent line? What comes right after this y? Yeah, f prime of a, and what's my f prime of a gonna be here? What did you? -3/8, yeah. So my f prime of 4, that gives me the slope of my tangent line is -3/8. And then what's my a? What's my x minus gonna be? 4, right? I'm going through that point right there. And then what's my b going to be? -2, yeah. There we go, that's it. That's the equation of the tangent line, and what better way to finish up class here than by confirming that we didn't do it completely wrong. All right, so what did I get here? Y equals -3/8. X minus 4 plus that -2. Bam, there it goes right through it. We did it. Yeah, we found the equation of a tangent line. It's kind of interesting, but this thing is actually kind of closely related to, maybe I'll talk about it later, but you know how when you purchase things online, you have like a secure connection that uses cryptography and things like that? Maybe no. A lot of the cryptography algorithms actually use implicit differentiation in a certain form to make your communications secure. So it's called elliptic curve cryptography. It's kind of neat. All right. Yeah, it is scary. It is scary. I know. Yeah, before when I was in my PhD program, I spent a lot of time teaching cryptography. I feel like I've seen a shorter way to do this. Yeah, there is a shorter way to do it. I'll go over it, Sydney. I'll go over it. I used to teach cryptography quite a bit. Whoa, wow, Sydney, is that a real lightsaber? Oh
Yeah,
man.
I got it for Christmas.
Wow. Oh my goodness, the force is strong with this one. Okay. All right. Any questions for me before I hang up? You know, I once did a lightsaber battle with my then 3-year-old son. I said it was like fighting Yoda. My sister like then like put orchestral music to it and like made like a cinematic thing out of it. Yeah. Yeah, we totally nerded out. Okay. All right. Well, okay. Bye everyone.